Hey guys, so we're going to do this worksheet that I gave you on Friday. I'm going to walk you through it to help you understand to make sure you're ready for tomorrow's test. So first off, we need a periodic table. So make sure you've got that handy. Okay. So the first one we're basically calculating the different subatomic particles. Okay. So for calcium, the symbol is element number 20. So the symbol is Ca. And this has a mass number of 41, so that's what goes in the upper right corner there. And then we can also put the atomic number on the bottom if we want to be complete. It's not necessarily required, but a lot of people do. Atomic number is equal to the number of protons, and I can get to the number of neutrons just by going mass number minus protons, because of course the mass of an atom is just protons and neutrons. So if we know protons, we can subtract it from the total mass. And so we would get 21 right there. The number of electrons in an element is always equal to the number of protons. We learned about ions, but this particular chart is all about elements, so we're not going to have any unbalanced protons and electrons. Okay, so atomic number 26, I look on the periodic table, and that is Fe, which we talked about in class, is iron. And so atomic number 26 means that there's also 26 protons and also 26 electrons. So that atomic number tells us a lot of information about the subatomic makeup of this particular substance. And then the mass number is just going to be the neutrons plus the protons. So that would be 31 plus 26. And so we get 57. Okay, I'm going to change the ink color so maybe we can differentiate these problems a little bit. The next one has a mass number of 13 and 5 protons. So we want to look on the periodic table for whatever has 5 protons. And that, of course, is boron, B, because it's element number 5. So the atomic number and the protons match. Also, if this is an element table, which it is, that means the protons and electrons match. Finally, for figuring out neutrons, it's the same deal as it was up in the calcium. We're going to take 13 minus 5 to get the number of neutrons, which is 8. Okay, so the last one in this table is Hg. Oh, that's mercury. So we talked about that in class a little bit as well. The 200 tells us the total mass of this particular piece of mercury. And I got to look at the periodic table to find the atomic number. Let's see. Oh, it's number 80. And that means there's 80 protons and also 80 electrons. And so then to get the number, the mass number here, we can use the mass number rather to figure out how many neutrons there are. So that would be 120 neutrons. Okay, so there's definitely be a problem like that on your test. Make sure you study that. The next one is about Rutherford's gold foil experiment, which we talked about extensively in class. And remember, you are not going to tell me that it was a laser, right? It is a particle beam, an alpha particle beam. Okay, now you can explain this either with pictures or a diagram kind of thing, or you can use words, depending on your own, outlook and preference. One of the conclusions that Rutherford made is that atoms are mostly empty space. Remember from the video that if you had the center of an atom the size of a marble, the rest of the atom would occupy the size of a football field, and it would be basically empty. The reason this was true is that most alpha particles, that's the alpha sign, you can also write out the word, went straight through, undeflected, we'd say. The second piece, conclusion that he drew was, so the second conclusion is that the center of an atom is very dense and positively charged. And the reason for that, we call that center a nucleus now, so you could also say nucleus if you wanted to. But the reason he thought that was true is that the Basically, the reason for this is that occasionally or very rarely a positive alpha particle was deflected or reflected. Those are the ones that bounced all the way back towards the source. So we have evidence and conclusion to support each point here. All right, so the next question, why aren't the masses of each element on the periodic table whole numbers? Like, for example, carbon is 12.011 something. The reason for that goes back to our discussion about the fact that, this is our example here, that say there's two different kinds of carbon. There's carbon 14 and carbon 12. Carbon 12 is the most common because the average mass, right? So the periodic table is an average mass of all isotopes, meaning all different types of carbon. So when you have an average mass, it means it's not going to be a whole number. That's not the same thing as the mass number, which is applicable to just a particular particle, which is what we're showing when we have isotopic notation. Okay, so Mendelev's periodic table is the basis for our current periodic table. Why is he considered the inventor and not many of the other scientists? We talked about de Chantois and Newlands, and also there's another guy, Lavoisier, that all had different kinds of periodic tables before him. And the reason that Mendeleev gets the credit is that he organized it by properties, like reactivity and density and all these different things. And most importantly, he found the holes, he found the missing places for elements to go, and that gave a revolutionary sort of motivation to people to look for new elements. The main group elements are the ones that are in groups 1, 2, and 13 through 18 on the periodic table that I gave you. Different periodic tables number the groups slightly differently, so make sure that you're using the one I give you in class, because it's what you'll have on the tests. But basically, you can imagine if this is a sketch of the periodic table, the main group elements are the ones that stick up tall, like that. The ones in the middle we called transition elements. Okay, so those ones are not the main group. And then this question, when 10 molecules of hydrogen react with oxygen, it either uses, so if we had 10 H2s, it would react with 5 O2s, or, let's do this other reaction in a different color. Let's see, blue. Or it can react with 10 molecules of O2. Now this kind of question sounds more difficult than it is, so don't get caught up in the details, but remember our discussion from class about the fact that you can kind of change the proportion of elements in a compound, and when you do, you get different elements. So in this particular example, if we had 10 oxygens, 10 hydrogens like this, well, actually, hang on a sec. It would make 10 of them. It would produce 10 hydrogen peroxides. Or if we had a 10 to 5 ratio, it would of course be making water, because there's 2 oxygens for every, 2 hydrogens for every 1 oxygen. So this means that in one case we're producing a compound of water, in the other case we're producing a compound hydrogen peroxide. So this is the law of multiple proportions at work. Right? We can vary the proportions of different atoms to make different compounds. Hydrogen and oxygen don't always have to produce water. You can produce a lot of other different things. Okay. All right. Number 6. Can 2 different elements have the same atomic number? Well, atomic number tells us, not atomist, I don't know what that means. Atomic number tells us how many protons something has. And we said that an element is defined, its properties come from the number of protons it has. So the answer here is no. 2 different elements have to have different atomic numbers. Otherwise, they would be the same element. Even if they have a different number of electrons or neutrons, it's still the same element because it still has the same properties. The protons are what give something its physical and chemical properties. Right? And so this is one of Dalton's principles. Dalton said that you can't turn oxygen into nitrogen in our diagram. And so that basic sort of principle, once we discovered what protons were, we learned that that principle is true because you can't change the number of protons something has. All right, number 7, the atomic mass for the natural isotopes of neon are as follows. So neon 20 has an isotope value that's very close to 20. 21 is very close to 20. Okay, so these numbers must be the masses here. So we have neon 20, neon 21, and neon 22. So even something as non-reactive as neon, it's a noble gas, so you know it doesn't really react with anything, has different isotopes. The periodic table says the mass is 20.180, which is very close to 20. So that means that neon with a mass of 20 is the most abundant. Remember, the word abundant also means most common. All right. And so, oh, this looks like a periodic table question. We played periodic table Battleship several times in class, and so this is basically that kind of question. All right, so group 8, the groups go along the top, so that means group 8 is kind of dead center in the periodic table, like in the transition elements. And period 4 is the first row of the transition elements. The element symbol for that is Fe, which is the element iron. Group 18 is the very far right group, and period 4, oh, that's the same period we were just in. That symbol is Kr. Well, if I'm not sure what that is, there's a listing in the book of alphabetical elements, so it's by, symbol, and I can just find the listing. But that one is an interesting noble gas because it's called krypton. Superman fans might have heard of something similar before. Okay, and then group 14 is the one that has carbon in the beginning of it. Oh, and period 2, that is carbon. Okay, so C, carbon. Okay, so that's how we play periodic table Battleship. All right, so if you have any questions, feel free to email me. I'll see you tomorrow.